Sample 6.1 of the book Design and Analysis of Experiments of Montgomery. The example is the next one. A 2-to-3 factorial design was used to develop a natural etch process on a single water plasma etching tool. The design factors are the gap between the electrodes. This is going to be factor A, the gas flow, factor B, and the RF power applied to the cathode. That's going to be our factor C. Each factor is run at 2 levels and the design is replicated twice. The response variable is the etch rate for the silicon nitride. So in the next list, you can see the factor levels, the low and the high for factor A, B, and C, as well as you can see the data of the problem and the coded factors of A, B, and C, and the runs they make. So we're going to copy this table on Excel. I already have it here. So we're going to start solving the problem. Here is the total. You need to add the total of the replicates. So it's simply add the answer of replicate number 1 plus the answer of the replicate number 2. And we scroll down. Then we're going to do Yates algorithm 3 times. This is because we have 3 factors. So Yates algorithm is really easy, is to add or subtract a pair of numbers. 4 plus the third, the 6 plus the 5th, the 8th plus the 7th, the second minus the first one. Once we already finish adding everything, the fourth one minus the third, the sixth minus the fifth, and the eighth minus the seventh. And we're going to copy this right here. That's it. This column, the last column of Yates algorithm, is our contrast level. Here, this number is our grand total. So we need to estimate the effect of each of the factors. And the formula is the next one. Is n times 1/2 times 2 to the k, n being the number of replicates and k being the number of factors. So we have here, that is the contrast over 2 times 2, because there are 2 replicates, times 0.5 times 2 to the third, that is 8. And here we have it, and we just scroll down. Then to know which factor cause a significant effect, here you can have more or less an idea. That is factor A and factor C and factor A, and the interaction between factor A and C. But to be sure, we need to do an ANOVA table. So we need to have first to calculate the sum of squares. So the sum of squares of the factor of interaction is the contrast square over n times 2 to the k. So we go back to Excel and have for factor A is a contrast square over n, that is 2 times 2 to the 3, that we said it was 8, and this is the sum of squares. And we are just going to scroll down. Then we need to calculate the sum square of the total. Here you need to have the sum squares of all the data minus the grand total squared over n being the number of all the data, that in this case is 16. So we have here in Excel a formula called suma de cuadrados. You select all the data, then minus grand total squared over, we said it was the number of data that we have, and we have 16. So this is the sum square of the total, and the sum squares of the error is subtracting from the sum squares of the total the sum of all the sum squares, and here we have it. Then the degrees of freedom for each of the factors and interaction is always 1. So we'll put a 1. Then for the degrees of freedom of the total is the total number of data, that is 16, minus 1. And the degrees of freedom is the degrees of freedom of the total minus the sum of all the other degrees of freedom, and in this case it gives me an 8. The mean square is really easy to obtain. Here we have the formulas for the degrees of freedom, and that is the mean square of the factor interaction, and for the error is the sum of squares of each divided by the degrees of freedom of each. So we're going back to Excel, and is sum of squares divided by degrees of freedom. Scroll down. Finally, the important part, everything is important, but here we are going to have the f-test. So here we need to divide the mean square of the factor or interaction divided by the mean square of the error. So here we have the mean square of the factor divided by the mean square of the error. We're going to select it. It's 18. And here we have it. It's not necessary to do the f-test for the error, just for the factors and interactions. And we're going to compare these values with the values of the f-test that we will have with a probability of 0.005, 1 degree of freedom, and 8 degrees of freedom. The 1 degree of freedom is this degree of freedom, and the 8 comes from the degrees of freedom of the error. So we compare to know if it is significant or not these two data. If the f-test value is greater than the f that should have, then it is a significant value. Having this, we can observe that factor A is significant. Also, factor C and the interaction between A and C are significant as well. So we can make a regression model for those factors. The regression model is the next one. You have the expected value equals to the average of the values plus the effect of A over 2 times minus or plus 1 plus the effect of C over 2 times minus 1 or plus 1 depending of this table, and the effect of the interaction between A and C over 2 times the multiplication of these -1 and -1 or 1. So I copy the data. The average is just the grand total over the number of data, that is 16. So we have it here. And I already copied the values, so I don't think there's more, I don't need to explain that. But here, for XA, it's -1, 1, -1, 1, -1, 1, -1, 1, because it's the code order of that factor. As well as here, you can see that C, there are -4 -1s, and then 4 +1s that are the same that you can see here. Then X of A and C is the multiplication of this XA and XC. So you have it here, and then in this cell you just do the operation, that is the average plus the effect over 2 times -1 plus the effect of C over 2 times XC plus the effect of AC over 2 times XAC. And here we have our expected results. Then we need to do a residual table. So here are the expected. We're going to copy these values. Just values. And then the observed one. We have 2 replicates. So to the observed values, we're going to use the average of these 2. And then to find the residual, we are going to subtract the observed minus the expected. And here we have our residual table. So here we copy the residuals, just values, and the contrast that is right here. Oh, sorry, right here. Oh, I didn't get the 1, so it is all of the column. Sorry about that. You have it here. So we're going to order it of the -20 and order from the lowest to the highest. So we have the lowest, we have the highest, and we assigned a place. That is 1, 2, 3, 4, 5, 6, 7, and 8. And then we are going to calculate the probability. That is 1, that is the place of it, minus 0.5 over the number of information, number of data, that is 8. And we have this. Then we need to plot it to know if it is the normality test. And yes, we can see here a line. It's not as straight as it is, but it shows a normal behavior. Normality test. I'm going to write it down here. Normality test. That's right. Then we are going to calculate the variance and the dispersion effect. So we have here a table of the factors, and it's coded values. So for A is this one, for B is this one, the interaction between A and B. You can find this table on internet, or you can do it yourself with this table that you already have. You, for the interactions, you just multiply each of the values and it gives you something, and then you copy the residual according to the factor or the interaction. So here you have. Then the variance of the positives of A is bar point S. It's very important point S because it is a sample, and it's this one times, and you select then this one that is positive and positive, and here you do the same but for the negatives of A. That is this one, this, and this. Then to have the dispersion effect, you calculate the natural logarithm of the variance of the positive value over the variance of the negative values, and you have minus 124. And to do this quickly, I already made this table here, so it's just a matter of patience. You need to pay attention to select correctly the data in the variance effect, and you can see here that only A, C, and the interaction between A and C has a dispersion effect. And here you see that the dispersion effect is less in the positive A and positive C, but it is less in the interaction between A and C. After that, we do a dispersion effect chart. We graph it, and here we can clearly see that AC and AC has a dispersion effect. So we we graph A, B, and C, and here we have the effects. You can see that there is a more dispersion on the minus negative one than to the positive one. So in conclusion, we need to maximize the etching of silicon nitride, we need to use the highest value of factor A. For factor B is the same, so we need to choose the cheapest option that we have. And for factor C, as we can see here, we have a larger dispersion on the lowest number and a lower dispersion on the highest value. So in conclusion, to maximize the etch rate of silicon nitride, we should use as factor A 1.20 centimeters, that should be the gap. For factor C, we need to use the cheapest one. So as you need less material, we need to use the 125. But for the factor C, we need to use the highest power to have less dispersion and less variability, and that is with the 325. So this is the end of the video. I hope you understand how to solve 2 to the 3 factor factorial.